share the screen also. So, small question in the chat about the group work. It's not mandatory to work in groups. You can work solo if you prefer that. And you form your own groups also. So we don't get our noses into that in this course. You are free to work with whomever you want. So let's leave the administrative informational part and start trying to learn something new, maybe, or at least repeating something old. So, as software developers, we you submit for grade 3 and 4 towards the end of the course. So passing grade is for the peer review and stuff, and the deadlines for the peer reviews are for passing grade. So as software developers, we do a lot of things to get our systems up and running. What do we do? What will you be working with in about maybe a year or two? Nothing? What? Millionaire. So how will you become millionaire? That's a good question. So what will you be doing when you go to your workplace in maybe 2 years or something like that? What do you think that you will be doing? Developing, and by developing you mean programming. Yay, that's a good thing to do, especially as you're supposed to be web developers, I guess, or something like that. And programming will hopefully at least be one of your tasks. So in fancy language, we call this implementation. I will write a short version of it there. So maybe implementation also is a bit broader than just programming. It can be fixing maybe even images for a system. You need images for stuff like that. That could be implementing something, database scripts and stuff like that. So implementation is maybe a little bit broader than programming, but for you guys, I think that programming, hitting the keyboards as fast as you can to produce if statements and stuff like that is what you will be doing. So you're at work and doing some implementation. Is that all that you will be doing? Do some planning, yeah. I will write, planning is actually something that everyone says. I usually don't write it down, but I do this time. Planning. So you're probably working in a project, and this project has a start and it has a finish, and you need to know when to do things and with whom and synchronize and stuff like that. So you need to do some planning, of course. Hopefully you won't be doing planning all day and every day, as little as possible, maybe even. Something more that you will be doing? So, okay, let me ask this question. How do you know what to implement? Yeah, absolutely. You need to break down the system. That is also good for planning. But how do you really know what the system is about? Analysis, exactly. We need to do some analysis. So, and you can maybe find that out from the course name also. And maybe the breakdown that you were talking about was the design part. Yeah, of course. But that is actually what design is very much about, breaking down a problem so that we can devise a solution, and we can also divide this solution among the project members so we can plan it in a good way. And then hopefully everything will fit together when we are done for the day or the week or the month or whatever time span we are thinking about here. But actually, before you can do any analysis and design, you need to know something more. And we have it here on the chat. We have requirements. Requirements. So somewhere someone needs to have an idea about what the system is about. What is the problem that we are solving actually? What problems do the customer have or do we have in our organization, and how should this system provide functionality to solve that problem? Because this is where it starts. Most of the time we don't do software development just for fun. It's not a hobby, it's a profession. So somewhere you are solving a problem and making stuff more efficient or better in some other way for someone else. So, and this is captured in requirements. And based on requirements, you can do analysis, and that's about understanding the requirements, understanding the problem. This can be a really, really hard task because you are probably faced then with problems that you do not work in yourselves. Maybe you will be working in a banking system with interest rates and loans and lendings and funds and stock options and stuff like that. You need to understand that domain before you can break it down and implement something to support the customer. So one key challenge for software engineers and software developers is that they need to be really good at implementation, understanding software and what can be done with it, as well as understand the problem of the customer. So you need also to understand the problem domain of the customer. And analysis can help us in this respect. So, okay, we kind of like know what to do and how to do it. We have planned and we are doing some implementation. What do we need to do more? Are we done? Testing, exactly. I don't think that the process of software development is finished without testing. So we need to work on test, and that is to find out if the implementation actually fulfills the requirements as they should and solves the problem ultimately of our customer. And the ultimate test is to get the end user actually to use our software. So we need to also to deploy. So basically this is what you will be faced with in your working lives. So you will be doing requirements, you will be doing analysis and design, implementation, test, and deployment, and some planning. And hopefully you have all already done a few of these activities, maybe more, maybe less. In your laboratory work in programming courses, you often get the requirements. This work should be doing this. You should do the, I don't know if you do the recipe database in the C# course still, or is it some other task? Okay, Mats has switched tasks then. So, but you get some, the system should do this, it should do this, it should do this. Maybe you haven't done very much of analysis and design, maybe not on paper at least, but in your head you have probably done some kind of breakdown of the problem to know how to start implementing it. You can't just hit the keyboards in some kind of a random fashion. Or maybe you have started implementing something and realized that, oh, this is not going to work. This became too complicated, or I went in a way that made things bad for me, and you had to go back and redesign, and then you could continue. Maybe you have sketched something on paper, maybe you haven't, but you have probably done analysis in design, but maybe in your own heads. Because you have probably not been working in a group setting where it becomes more important to communicate this stuff and planning and breaking down and giving different parts to different people. Also in university and in schools, we tend to use systems and requirements as examples that are easy to understand, that you already have some kind of experience with. Mathematical problems are popular often because you don't need to spend a lot of time understanding the problem itself. It is more or less already provided to you or assumed as basic knowledge to know how what the recipe is or something like that. So you don't really have an advanced or complicated problem domain because time is limited for us. And you have done a lot of implementation, I hope. Hopefully you have tested before you have given the laboratory work to your tutors. Unfortunately, they often find problems anyway. So we are often notoriously bad at testing, and it's hard also to test your own code. Because if you had thought about it, you would have kind of like implemented something that made that test unnecessary anyway. So it's like a little bit of a catch-22 to test your own code. And there are processes and development methodologies that reverse this, test first and stuff like that. And hopefully you have managed to also deploy your software, maybe at least to your laboratory tutors, so you could have finished the course in some way. I'm putting planning a little bit in parentheses here because it's of course part of a software process, but not the maybe the core of what you have been doing so far, at least. So if you follow this process, you do find out all the requirements. You talk to the end users a lot, and you write all the requirements down, and then you do the analysis to understand the problem, and then you do a full design of the system. You divide it into different parts, and you hand it to the programmers. They do all the implementation, and then you enter the test phase, and then finally you deploy your big system. You have a process, and do you know what this process is called? It's the most basic process maybe. It's the waterfall model. So this model is can be good if you are really sure about your requirements. If you have a very stable problem domain, it could be a good process. If you have a short project, a few weeks, could be very efficient. But it's also very risky because it's hard to get the requirements right. No matter how much time you spend doing requirements, things are kind of like bound to change in unexpected ways. Therefore, the waterfall model is not that popular, especially in domains where you have like the general public as the end user, because the opinion of the general public can switch and sway really fast. so you need to be more agile. So you need to do all these stuffs, but you can't find out all the requirements, and it's unnecessary because when you have come to implementation, 90% of those requirements have already changed. So instead, we are talking about iterative and agile development. So if we have time here on this axis, we will be doing some requirements, and probably we will be doing a lot of requirements at first, and it will probably dwindle a little bit towards the end. Something like that maybe. And also analysis a little bit more at first, and probably not as much towards the end. And the same for design. Implementation, a lot of implementation. We like implementation. So, and testing also. And this kind of like becomes a little bit natural, because if you don't have that much code to test, well, you don't need to put that much effort into testing. And when you have a lot of code to test here, well, then you need to put more effort into testing. So there definitely will be testing in the beginning, but it will be more and more towards the end. And deployment will likely also require not as many resources in the beginning, but a full system deploy towards the end can be quite a task. So something like this. So given a day, a point in time, you will be doing all these activities. Maybe this is one day in the project, in the at least first half of the project. You will probably be reading some requirements, updating requirements, fixing them, making them better. You will be maybe looking at some design. You will be doing analysis. You will be doing some design, some implementation, adding some tests, doing some deployment. And as days goes by here, the system grows incrementally, hopefully, until it reaches a good enough size for to become finished, more or less. The term finished in software is also a little bit awkward, because there is always things to do. If your software is used, it will need to change. That is how it is. But this process of understanding what to do, how to do it, test it, and deploy it is something that you will do. But you will probably do it during a day or during a week. And this is the iterative and incremental approach to software development. I don't know if this diagram is familiar to you. Have you seen something like it? Yeah? Good. I think you have had the software development course with Jesper or something like that. So this should be old news. So we can see here where when we do object-oriented analysis and design, focus is more towards the beginning of the project. Hopefully we can establish a stable design somewhere in the first half of the project at least, so we know this is the way that we divide things. And we can use this framework or skeleton to add our more and more detailed design. So we don't need to work on it, hopefully, at the end, because doing a major revision of the design here, because we found some problem, can be very, very troublesome. Because then we need to maybe throw away a lot of code, and we need to retest a lot, and stuff can happen. So focus is probably towards the beginning, but it is something that you will probably do every day. So Time moves fast. Next question is, why do analysis and design? Well, you can't really get away without them. But more specifically, maybe you do them in your head if you have a really, really small problem. But small problems are not that interesting, and they are easier to handle overall. So when you're faced with something that is a little bit larger, you run into problems. So let's take a look at the far end of the spectrum. Do you know what this is? Can you find the bug? Probably not. Can you correct the bug? Probably not. Can you collaborate doing something on this software? Probably not. Because this is actually what the CPU needs to get for our system to work. This is executable machine code on the x86 processing architecture. So this is what is fed into the processor, and it can do various stuffs. So it's simply an executable file that I have opened in a text editor. This is what the CPU eats. And as you see, well, maybe you can do something in machine code. Maybe some of you have been programming something in machine code, but it's quite limited what you can do. Collaboration becomes really, really hard in this form of a software. So this is not something that we would really like to work with. So this is maybe something that you won't be seeing so much about. But this is what your systems are transformed into. Even if you have the source code and it's interpreted instead of compiled, it is somewhere in your processing pipeline converted to this. So the next level of abstraction, so to speak, is to take a look at the source code. And source code is something that we can at least read, but in a system that is not very large, but fairly large, and maybe larger than you have worked with so far, you have a lot of source code. And, well, you can read it, and maybe you can find something in it to understand it, but it's quite hard anyway. Because you have these files, and they have functions in them and variables, and just to understand this, what is this also all about? Well, it's not that easy to find out what this is. This is like 1,500 lines of code in this file alone. And there are a lot of files in this project. So understanding a software from this perspective can also be really, really challenging. And especially if you just come to a system that is, you have something there already, and you come as maybe a new developer. So, okay, you should start contributing now, and you should fix this problem or implement this requirement, and we need this feature. Oh, where to begin? Well, maybe I will just start looking here. Oh, could this be it? It's not that easy. So source code is fine and dandy, but it can be hard to understand, especially if the system is big. And this system is not that big, really. So, but it becomes complicated very, very quickly. However, if we can get a image like this instead, that does not have that many parts, but it's rather a very abstract view on the system. We can start to understand things more quickly if we know what these arrows and boxes mean. This is something that we can comprehend much, much better than the source code. And we can divide it into different parts so that different developers can work on different parts and they can fit together. And maybe even developers can become experts in different areas here. So maybe one developer likes to do rendering, so he works mostly in this part of the system. He's an expert on that. So we can allocate resources more efficiently and plan and understand better. So this is called the semantic gap. So over here we have the CPU, we have the processor, and it eats this machine code, and so on and so forth. And this is something that we really can't understand. And here we have the source code, if statements, stuff like this. And this is transformed into the machine code, and this is done automatically. That's good. So we compile, or we have an interpreter that translates our if statement into this machine code. And we have these diagrams to help us understand the source code, divide it into appropriate chunks that can be assembled and developed in parallel. And before that, we have another set of diagrams that look a little bit the same, but mean something different. And this is to understand the problem. So using problem understanding, we can come up with a technical solution that is based in reality. So it becomes even easier to understand it, because if you know what this system is about, you can see this reflected in the technical solution and in the source code. We often see this as good names for classes. And here we have the dude that has a bright idea. And to understand his idea, we take his requirements and we transform them into an analysis model, and the chain is complete. So instead of taking this, maybe I should write this in a different color. Instead of taking this giant leap from idea to machine code, we take smaller steps instead, so that we can add functionality and add quality in each and every step. For example, we can develop things faster by dividing the problem into good parts, so that we can have 5 programmers working on it instead of just 1 programmer working in machine code, or 1 programmer working in 1 large source code file. And also, this provides us with the opportunity to find problems. Ideas and requirements are fine and dandy, but they are always wrong in some aspect. There is always something that is overlooked, not communicated properly, maybe communicated ambiguously. This user says this thing, this other user says another thing. Do they mean the same thing, or do they just use different words for the same thing, or are they in conflict and stuff like that? So analysis provides us with the opportunity to find problems in our requirements. And we have this feedback loop also here. If we find some problems in the source code that, okay, we cannot actually do this as we had planned, we feed this back into the design and find that, oh, we need to change this in our design also, in our blueprint. And this could be fed back all the way to finding a problem in the requirement. And ultimately, this is what we would like to not have enter our source code. We would not like to ship bugs in our source code. So this is why we do analysis and design. Time is moving fast, so I think we will be doing the dice game example in the next lecture. A little bit unfortunate, but things are like this sometimes. So next thing to maybe take a look at. We know when to do analysis and design. We know why we do analysis and design. We know a little bit about what analysis is. It's about understanding a problem. And design is about devising and dividing a technical solution for the problem. So the next step is why use object orientation to do this? You can do analysis and design in several different ways, but object orientation has come up as the at least most basic level used these days. You can have more advanced technical solutions and ways of doing analysis and design, but they often all build on the principles, at least, of object orientation. So there are three major parts of this. The first thing is abstraction. As humans, we don't really like details. Or rather, we like details when we need them, but we would like to have as few details as possible for our current needs. So, for example, you are walking along the street and you are crossing the street. You're not really interested in the car model that's about to hit you. You're not really interested in its color, what kind of driving the wheels has, and how much fuel is in the tank, and so on and so forth. You're mostly interested in, oh, something big is moving towards me really fast. I better jump out of the way. In another scenario, for example, if you're at a racetrack and studying a Formula 1 race, it could be really interesting to know how much fuel has this driver actually left in his tank. When does he need to go into the pit stop to refuel? Will he do it now, or will he wait one more lap? How much fuel will his car consume? How much wear is on his tires? Will he change tires now, or will he wait? Then those details are really, really interesting and useful for you. So we need some way to support this way of finding abstractions and be able to have details when we want them and reason about things in an abstract way. This is something that we need to have to better understand problems and devising technical solutions for them. So to be able to reason about the problem at the right level of abstraction is one of the key strengths of object orientation. We have this built into object orientation, and it supports the human way of thinking about stuff. In some parts of your system, when doing some tasks, you need really, really fine-grained details. When reasoning about other requirements in your system, you need another set of details. So this is something that object orientation supports, abstraction. The next thing is encapsulation. So this is kind of like connected to abstraction also, because we can achieve abstraction by using encapsulation, but it's a little bit different. How many of you have a driving license? Most? How many understand how a combustion engine really works? So. But you can drive a car really, really well without knowing the intricate details of fuel injection. You don't really need to understand that. So what we have done here is that we have taken something that is really, really complicated. We have packaged it, put it together, and we have slapped a standard interface on it. So as long as this has a steering wheel, gear shift, some lights and stuff like that, you know how to drive it. Maybe not perfectly the first few moments, but you get the feel for the car really, really quickly, and you know how to drive it. You don't need to know all the details of the engine and stuff like that to drive the car. So this is something that we also would like to support in software, of course. We would like to take something that is really, really complicated, a lot of if statements, and put it in some encapsulated form that you really should not open and look at, but you can use it. So you can use a library for video compression without really understanding how video compression really, really works, because it's really, really complicated. So encapsulation is something that we would like to have also, and this is what object orientation provides us with. There are other ways to get encapsulation also, but object orientation supports encapsulation. And lastly but not least is hierarchies. So, as humans, we like to build hierarchies of stuff. We like to understand things by connecting them with each other. So, if you know what a leaf is, which is a part of a tree, you can understand a leaf on a bush, and you can understand a straw of grass, because basically they are the same but different. So you can have this whole part hierarchies of stuff. And we know the basic parts of a car. We have the wheels, and we have the engine, we have the fuel tank, and we have the steering wheel. So by understanding the fuel tank in a car, we can understand the fuel tank in an airplane and in a motorcycle and something like that. So we build this whole part hierarchies. And we also build is-a hierarchies. So when reasoning about problems and stuff, we also like to consider the highest level of abstraction by saying that, well, I need a vehicle to take me from here to Gothenburg. So I need to find a vehicle suitable for my needs. So what kind of vehicles do I have? Well, a bicycle is a vehicle. It could provide me with transportation from here to Gothenburg. It will take me a long time, but I will maybe get exercise also. So it has pros and cons. I could go by car. It will be a lot faster. I don't really like driving. It's bad for the environment. So it also has different qualities, but it's a vehicle. I could maybe go by train if I would not like to arrive at all. I have an interesting question here in the chat about functional programming. And in specific scenarios where functional programming is a better choice. I think these are all tools that we need to understand and use in our toolbox. And functional programming, well, it seems to be the popular thing right now. And you can probably find the support of the abstraction, encapsulation, and hierarchy in functional programming also. And in some respects, it will be easier. In other, it will be harder. So I don't really see it as a big, they are not opposites, but they are different tools to provide the same kind of stuff. I cannot really find specific scenarios. Are of course if you have an environment that is already made with functional programming, you should probably continue that and not switch to an object-oriented approach instead. The main advantage of functional programming is the really strict way of handling state in your application, and that's a good thing. In object-oriented designs, if done wrong, you can have a lot of state problems. So, well, I don't know if that's really a good answer, but it was one answer at least. So, these are the qualities that we as humans use to understand problems and work in our daily lives. This is what you do to get by. You can't really focus on every minute detail in every instance of stuff, because then you would not survive, I think, because we are get so much information from our senses all the time. So we need some way to abstract, encapsulate, and build hierarchies to understand our world. And this is what object orientation is also supposed to bring us. It's supposed to make things easier for us, not more complicated. So, lastly but not leastly, we have the UML. So, Unified Modeling Language. It's a language to make models. It's not limited to doing object-oriented models. The UML is really big. You have a lot of support for a lot of different aspects. It's focused on software development, but it's not restricted to software development. You can use UML to enhance your business processes and stuff like that. You can use it to model requirements and things like that also. In this course, we will be focusing on the analysis and design parts of the UML, and one big large part will be making class diagrams in different ways. But it's unified, and this comes from a time where we had the language wars, a little bit of software development history. When I attended university, kind of like in the 90s, I think 98 or something like that, we had the language wars. You had these bearded guys, they still exist, bearded guys, and they are the gurus of our field, and they all had their own way of doing this. So one guy, he did clouds. He drew clouds. And another guy drew boxes. And they were kind of like the same, but it was really a pain in the ass to draw clouds here. And they were also supposed to be clouds that looked like this. They had little holes in them. So that was really a pain to draw. This is the notation that I learned when I attended. It was a Booch notation. But eventually they settled and collaborated and started doing a unified notation for this kind of stuff. And this is where the unified comes from. It's visual. One of the key points actually is that we are really good at processing visual information. We can spot minute errors and stuff like that in images, quite easy. We're not really that good at text processing. We need to read it, and it's hard to find problems. You probably have written some kind of essay sometime, and you have read it like 5 times, and then you give it to someone else, and the first thing they see is, well, this headline has a spelling error. So we're not really good at looking at text. So it's a visual language. And this also means that it's not a process. You cannot develop according to the UML. You can use the UML in your development process if you would like to. So it was made with the intent of being used in the unified process, but it's not restricted to the unified process. You can use it in a waterfall model project or in some other project if you want to. As soon as you would like to do some kind of sketching, modeling, you can use the unified modeling language. And you can have different levels of formality also. You can do really detailed stuff in UML, really blueprints, and give these blueprints to the programmers and they can follow them exactly. Or you could just do sketches to communicate the problem. Oh, we should have this class and it should be connected to that class, and well, you know what to do, guys, and throw it away later. So the UML, using the UML does not mean that we have these detailed blueprints. We can have them if we want to. Maybe we have them on a really complicated part of our system, but probably not the whole system, because updating that kind of really detailed diagrams is a pain. If you have good tool support, you can also generate code from UML. So you can do your models visually, drag the boxes and the arrows and click generate code, and you will have the skeleton of the application. And you can do vice versa also. You can take your source code and reverse engineer it into a diagram if you have good tool support. We will be doing this mostly manually during this course to understand it. So I think the time is running out. The next lecture will be focusing on domain modeling, and we will be doing a small initial code example just to see requirements analysis, design, implementation. So this is what we will start with tomorrow. Any questions? Good. Let's conclude then. Have a continuing nice day.